Here we go. So, let's get into some of these rules here. Let's try and figure some things out. One of the first rules we're going to look at here is called the constant rule. All right. So the first thing we'll look at is something pretty simple. We'll be looking at taking the derivative of a constant. Okay. So what is the derivative of y equals 7? Okay. And again, remember, the derivative is that thing that we get after we apply the limit definition of the derivative, right? After we do that limit as h approaches 0 of f of x plus h minus f of x over h, once we apply that to our function, that thing that we get as a result, that is the derivative. Okay? So in this case, y equals 7, that means our function here is really f of x equals 7, right? I wrote it as y equals 7, but it's the same thing, f of x equals 7. Okay? Now, when we evaluated this limit, right, or we saw yesterday that the origin of this limit, the reason why it is written the way it is, or one application of it, I should say, maybe, is that this is the slope of the function. Okay? The derivative also can be known as the instantaneous slope, or instantaneous rate of change of the function. You guys already know what the slope of this function is going to be. What is the slope of this function? 0, right? Because the graph of y equals 7 is what kind of thing? A horizontal line. And a horizontal line, we know its slope is 0. Okay? So we know the answer to this had better be 0. And in fact, well, you'll see it will be. So let's plug in here. Since our function is just 7, right, there's no x's here at all. So then f of x plus h is just 7. And f of x, well, that's very clearly 7, right? That's written right there. And then it's all over h. Right? Again, because our function's constant, it's unchanging, right? It's always 7. So f of x plus h is 7, f of x is 7, f of 2 is 7, f of 10 is 7, right? It's always 7. And so we can simplify this. What's 7 minus 7? 0. What's 0 divided by h? Still 0. And so what is the limit as h approaches 0 of 0? 0. No surprises there. Okay? We get 0. Okay? And in fact, in general, if a constant function is differentiable, and we won't worry about things that aren't differentiable. For right now, you'll learn more about that when you're in calculus. But, I mean, the word differentiable just means able to be differentiated. There are situations and cases where you can't take the derivative of something for a variety of different reasons. But if a constant function is differentiable, then the derivative of the function is 0. Put in mathematical symbols, put in like some typical mathematical symbols here for calculus. Okay. We can write it that way. And I'll show you how to read this here too. This little statement right here is read as, well, one way you can read it is the derivative of c with respect to x is 0. Okay, that's kind of how you read that. And I'll try and read through it here kind of piece at a time. So the lowercase d stands for the derivative of c. So the derivative of the stuff here in the brackets, the derivative of c with respect to x is this over dx part. Okay, the derivative of c with respect to x is or equals 0. And what that with respect to x part means is that it's kind of like right now when we take the derivative of something, we're always taking the derivative with respect to whatever variable happens to be a part of the function, right? So, excuse me, in the warm up here, right, it has x's in it, and so we're going to take the derivative with respect to x. There will be situations later in calculus where you'll have different variables mixed together, like x's and y's, for example, and you will potentially, you need to know then with respect to which variable you are taking the derivative. So typically it's x, but it can be other variables too, depending on what's kind of mixed together and stuff like that. But traditionally it's just x. And you'll see what happens when you have multiple variables and you're trying to take the derivative with respect to just one of them and stuff like that. But that's beyond what we need to worry about right now. Okay, so that's the constant rule. Pretty simple. Now let's take a look at the power rule. Okay? And this one, you can't predict the answer to as easily as you did the last one, but you will be able to figure it out with enough examples here. So I'm going to help you with that. Okay? So let's find the derivative of the following using the limit definition. That's that limit as h approaches 0 of f of x plus h over f or minus f of x all over h. All right. We'll do 3 of these. And hopefully with 3, you'll be able to get some of you guys will be able to figure out kind of what the pattern is here to help you be able to bypass this limit definition. All right, so first one, f of x equals x squared. All right, we know this from yesterday, actually. We did this. If you apply the limit as h approaches 0 of f of x plus h minus f of x all over h, you're going to end up with 2x. Okay, we did this for the warm-up yesterday. I'm not going to re-show that one. We did it for the warm-up yesterday. Okay. 2x. Now, one other way we can denote the derivative of something, of a function, is to rewrite that function, so f of x, and we put a little apostrophe there, but we read that as f prime of x. F prime of x. F prime of x stands for the derivative of f of x. Okay, so the derivative of f of x, we denote that with f prime of x, and that's 2x. Okay? Let's do another one. Let's do x cubed. All right, and I'll do this. You don't need to worry about doing it right now. So we'll take a limit as h approaches 0 of f of x plus h minus f of x all over h. And then I will actually do here. So f of x plus h means we're going to be doing x plus h cubed minus x cubed all over h. Oh boy, we could cube a binomial. That's fun. Well, I'll go ahead and do that for us here. This is going to end up being x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. All right. So hopefully you guys can kind of see the need for some sort of, or the hope for some sort of shortcut when it comes to taking some of these derivatives, right? Because we're up to x cubed, and that gets pretty ridiculous trying to cube x plus h and then simplifying all that mess. Imagine if we were doing like x to the 4th or x to the 5th or x to the 10th or something like that. Like you wouldn't want to have to multiply that out. So we're really hoping there is some shortcut here available to us so we can bypass all this crazy algebra we have to do. All right. That being said, we don't know the shortcut yet, so we have to keep simplifying. What can we simplify here in this limit? What can cancel? The x cubes. And so we're left with the limit as h approaches 0. That leaves us then with every term has at least one h in it. So I'm going to go ahead and factor one of those h's out. And so I'm left with 3x squared plus 3xh plus h squared all over h. The h's can cancel. That'll be the one h in the numerator that we factored out with the h in the denominator. And now I can direct substitute in 0 for h. When I direct substitute in 0 for h, what's left? What will be left here? If I plug in 0 for h now, what's going to be left? 3x squared, and that's it. Okay, that will be 0, so it's going to be 0 times 3x, gone. 0 squared is 0, so it'll be 0 plus 0 plus 3x squared, so 3x squared. Okay, interesting, interesting. So right now, we took f of x equals x squared, found its derivative. F prime of x was 2x. That was yesterday. We did that for the one. Today, we just did f of x equals x cubed, found its derivative, got 3x squared. We'll do one more here, and this one we did in the homework, so I'm not going to, again, redo it. The square root of x. Okay, if you remember when we did the limit definition here of the derivative of that, we end up with ... f prime of x equals 1 over 2 square roots of x, like that. Okay. Now, there are 3 derivatives here. Can anyone see any relationship between the original function and its derivative? Okay, Maddie, what do you think? Okay, right. So here we start with a degree of 2, and now it's a degree of 1. Here it's a degree of 3, and we end up with a degree of 2. Here we end up with a degree of, what would the power here be? Right, this is x to the 1/2. And then what's the power here? It would end up being negative 1/2, wouldn't it? Because if I rewrite the square root of x as 1 over 2x to the 1/2, if I bring that x out of the denominator, it's now 1/2 x to the negative 1/2. So sure enough, that still follows even here. Subtract 1 from the exponent, we get that negative 1/2. Okay, so that tells us how the power is changing. What else, though? There's other stuff that's changing, too. So yes, the degree lowers by 1. 2 goes to a 1. 3 goes to 2. 1/2 goes to negative 1/2. What else can we do here, Maddie? Yeah, the exponent becomes a coefficient. So 2x to the 2 becomes 2x to the 1. X to the 3 becomes 3x to the 2. X to the 1/2 becomes 1/2 x to the negative 1/2. Okay? And so that's exactly the idea. That is the power rule there. Okay? That's that power rule. And so in general, and I don't think I wrote this down for my other class, but I'll write it down here. Okay? The power rule is this. The derivative with respect to x of x to the n is equal to n times x to the n minus 1. That's the only problem. The next breeze is that it blows all my papers around. Gotta weigh everything down. Or just not have so much junk on my desk, too. Okay, so let's do some examples here real quick without using the limit definition. For example, we'll just our directions here are to find the derivative of each function. Okay, so number 1, f of x equals x to the 4th whole f prime of xb. Or x to the 3rd, 4x to the 3, 4x cubed, yep, just like that. Good. Number 2, g of x equals the cube root of x. What would g prime of x be? Are you all done there, Ann? Yep. Okay. Do you want to start on the other section now? Okay. All right, well, what is the cube root? What's the exponent if you have a cube root? X to the 1/3. So now 1 over 3.
Not cube, I mean like cube root.
Oh, I see what you're saying. Yeah, so let's just take care of the exponent, and then we can put it back under a cube root if you want to there. So the 1/3 comes out front. What's 1/3 minus 1? Ooh, fractions, negatives. Negative 2/3. Okay, so that's what it ends up being. Which, if you want to rewrite it then with the cube root and stuff like that, it would be something like that. Okay. But this is fine right here too. Okay. And then number 3. I'm going to do 2 more here. So this one and then 1 more. All right, how about 1 over x squared? What's its derivative going to be? Well, 1 over x squared is the same thing as x to the what power? X to the negative 2. So now, if we take its derivative, what will the coefficient be? Negative 2, x to the what? Negative 3, right? We've got to lower the power by 1. There it is. Okay, which is then the same thing as negative 2 over x to the third. So you'll see that part of the challenge, or part of the task of taking the derivative, is making sure that our derivative matches the rules that we have, right? We may get a little ahead of ourselves here. For example, some people may look at number 3 and say, oh, the derivative of this, let's see here, the derivative of 1 is 0. The derivative of x squared is 2x. So the answer is 0 over 2x. No, we can't take the derivative of this thing as it's currently written. All we know how to do is take the derivative of x to a power and a constant. This is not x to a power. This is 1 over x to a power. Different. So we have to rewrite it in terms of a form that we can take the derivative. X to the negative 2. That is x to a power. We can take its derivative, and we end up with this. Okay, so you do want to be careful here. We're expanding the number of derivatives that we can take, but we still have things that we would not be able to take the derivative of them. Okay, there's still lots of things of which we can't take the derivative. So anyway, let's do one more here, and this one's f of x equals pi squared. What will the derivative of that be? What will the derivative of that be? Now we have a rule that applies here. Of the rules that we've gone over for taking the derivative, we've only gone over 2. One of those rules applies here. Which one applies here? And what will its derivative be? So, Caroline, what is it? 0! That's right. Exactly right. It's 0. But Mr. Whitmire, it's pi squared. It should be 2 pi to the 1. It would be if it was x's. But since that's pi, pi is just a number. And I put that there on purpose because, we tend to think of pi as like a variable, or like kind of, it looks different. It's not, we don't really think of it as a number sometimes. But it really is just a number. Pi squared, it's a number. The derivative of a constant, or derivative of a number, it's 0. And so it's just going to be 0 there. Okay? Now, what about something like, what if we want to take the derivative of something like g of x equals 3x to the 4th? That doesn't really match our power rule, because we don't have a rule for when there's a number in front of the x here. All we have is when there's just x to a power. Here we have 3 times x to a power. What do we do here? Well, as it turns out, derivative with respect to x of a function that's being multiplied by a constant in front, so like here, right? Here we have x to the 4th being multiplied by a 3. That's equal to, the derivative of that is equal to just that same c times f prime of x. So in other words, we can kind of take this 3, separate it, in a sense, from x to the 4th. It's still there, but just kind of like, keep it separate. We can take the derivative of this x to the 4th, leaving the 3 out front, and the derivative of x to the 4th is 4x cubed. And then we can finish off by multiplying the 3 and the 4 back together, so it's 12x to the 3rd. Is that derivative? Okay? So really we end up just, when we bring that 4 out front, the 4 ends up multiplying with 3. So 4 times 3, x to the 3rd. So we get 12x to the 3rd there. Okay? And then one other thing I'm going to show you too, and that's if we have a sum or a difference of terms. Right? What if we want to take the derivative of like a polynomial? Well, as it turns out, the derivative with respect to x of a function plus or minus another function is simply the derivative of the individual parts added or subtracted. Okay, so as a quick example here, if we have like f of x equals x to the third minus 4x plus 5, we can take the derivative of this polynomial by taking the derivative of the individual pieces that are split up by addition or subtraction. Okay, so what's the derivative of x cubed? 3x squared. What's the derivative of 4x going to be? Ooh, we haven't done one like this yet, right? What's the exponent for the x right here? A 1. So the 1 comes out and multiplies with a 4 to give us 4. And then we lower the power by 1, which is going to be the power of 0. What's x to the 0? 1. So the x kind of disappears. When you take the derivative of 4x, you're left with just 4. Okay? So if I finish simple, oops, Mr. Widmeyer. What's the derivative of 5? It's 0, right? It's nothing, so I have a plus 0 there. My bad. So sorry about that. And so it'll be 3x squared then minus 4, and then plus 0 if you want, but really it's just 3x squared minus 4. Okay? And there it is. That is like a basic overview of some of the, rules for taking a derivative. All right? Questions on any of that? So I have a few problems that I want to give you for your homework, and then that's it. This is again your last homework assignment. All right. If you find next week that you're really missing the homework, I can try and come up with some more homework problems for you. But if you need that, so just let me know. Okay, and we'll get you some more homework problems. In the meantime, though, we'll get started here on this thing. Let's see, where did I put that? I think I put the assignment over here. Don't forget, you also have a problem set due on Monday as well. Problem set number 8 is that you're graphing the rational function. If you need another copy of that, I do have some spares here. So if you're missing your copy, you never got one in the first